Here is a cube. 6 faces, every one an identical square, and at each corner exactly 3 of them meet. Nothing about it is lopsided. So here is the question. How many other shapes are this perfect? Same identical faces, the same number meeting at every corner all the way around. Take a second and actually guess a number. The answer is 5. Not 5 that anyone happens to have found so far. 5, full stop. There is a proof that the 6th is impossible, and by the end, you will have watched it happen. First, the exact rules, because they are what make the answer finite. Every face has to be the same regular polygon, a flat shape with all its sides and all its corners, equal, like a square or a triangle. And the same number of faces has to meet at every single corner. One more rule, the shape has to be convex. That just means no dents, no part caving inward. If you can push a face in, it is out. That is the whole list of assumptions. And from just those plus one fact about counting, the answer is completely forced. So let us count. Every one of these solids is built from 3 kinds of thing: corners, edges, and faces. Watch what happens when you just count them and combine them in one particular way. The cube. 8 corners, 12 edges, 6 faces. Now take the corners, subtract the edges, add the faces. 8 minus 12 plus 6. That is 2. Try a completely different shape. The tetrahedron, 4 triangles, 4 corners, 6 edges, 4 faces. 4 minus 6 plus 4. 2 again, 1 more, and pick a strange one. The octahedron, 8 triangles glued into a diamond. 6 corners, 12 edges, 8 faces. 6 minus 12 plus 8. 2. 3 shapes with nothing in common and the same answer every time. Now you should be suspicious. Maybe 2 is just a fluke for the ones I happen to pick. So let us prove it is not. Here is the claim in full. For any convex solid at all, corners minus edges plus faces equals 2. Every time. Here is why you cannot escape it. Take the solid and cut one face right out, like popping a panel off a box. Now grab the edges of that hole and stretch it wide open, until the whole thing flattens down onto the table. You have not lost anything from the count. The face you popped out is now the entire region outside the drawing, so it still counts as a face. Every corner and every edge is here too, just squashed flat. Now, tear it down, carefully. Erase one edge that sits between 2 faces. You lose that edge, but the 2 faces on either side merge into one, so you lose a face as well. Corners minus edges plus faces does not move. The only other move you will need, find an edge sticking out with a loose corner on its tip and snip it off. Now, you lose an edge and a corner together. Same result. The total refuses to change. Keep going. Every step is one of those 2 moves and neither one ever touches the total. So peel the whole network away until there is almost nothing left. You end on a single triangle. Count it yourself right now. 3 corners, 3 edges, and 2 faces, the triangle itself and everything outside it. 3 minus 3 plus 2. 2, but the total never changed on the way down, so it was 2 at the triangle, which means it was 2 at the cube, which means it is 2 for whatever solid you started with. Any solid. That is Euler's formula, and you just proved it. Now we turn that one fact into a cage the solids cannot climb out of. Say every face is a polygon with p sides and exactly q faces meet at each corner. Our rules mean p and q are each at least 3. You cannot build a face from 2 sides or a corner from 2 flats. Count the edges 2 ways. First, by faces. Each face has p edges, and every edge is the border between exactly 2 faces, so it gets counted twice. That means p times the number of faces equals twice the number of edges. Now count the edges by corners. At each corner, q edges come together, and every edge has 2 ends, so again everything is counted twice. So q times the number of corners equals twice the number of edges too. Flip both of those around. The number of faces is 2e over p. The number of corners is 2e over q. We have just written the faces and the corners purely in terms of the edges, p and q. Now drop both straight into Euler's formula in place of the corners and the faces. Corners minus edges plus faces becomes 2e over q minus e plus 2e over p, and all of that still has to equal 2. Every single term has an e in it, so divide the whole line by 2 times e. Almost everything cancels and you are left with something tiny. 1 over p plus 1 over q equals 1/2 plus 1 over e. Now look at that last piece. The number of edges is positive, so 1 over the edges is some amount above 0, which forces 1 over p plus 1 over q to be strictly bigger than 1/2. That inequality is the entire question, shrunk to fit on one line. Stop and see what just happened. A question about solid shapes turning in space became a question about 2 whole numbers and 1 inequality. There is no geometry left in it. It is pure arithmetic now, so try the whole numbers, starting small. Let the faces be triangles, p equals 3. Then 1/3 plus 1 over q has to beat 1/2, so 1 over q has to beat 1/6. That lets q be 3, 4, or 5. 6 is already too far. Now square faces, p equals 4. 1/4 plus 1 over q beats 1/2 only when 1 over q beats 1/4, so q has to be 3 and nothing bigger. 4 squares at a corner already lands flat on 1/2. Pentagons, p equals 5. 1/5 plus 1 over q clears 1/2 only when q is 3. Once again, exactly one option survives. Then hexagons, p equals 6. 1/6 plus 1 over q, and even the most generous choice, q equals 3, only reaches exactly 1/2, not bigger. It just misses. And landing on exactly 1/2 is not nothing. It is the flat case. 3 hexagons around a point, or 6 triangles, or 4 squares lie perfectly flat and tile a floor forever. They never curl up into a solid. That is the door quietly closing. And any face with more sides than that only makes 1 over p smaller, which drags the sum further below 1/2. 7 sides, 8, 100, all hopeless. The list cannot grow, so count what survived. With triangles, 3, 4, or 5 at a corner. With squares, 3. With pentagons, 3. That is 5 pairs of numbers, and not one other pair exists anywhere. And every single one of those 5 pairs is a shape you can actually hold. Watch them appear as their numbers are called. 3, 3, triangles, 3 at every corner. That is the tetrahedron. 4, 3. Squares, 3 at every corner. The cube we started with. 3, 4. Triangles again, but now 4 at every corner. The octahedron, 5, 3. Pentagons, 3 at every corner. The dodecahedron, 12 pentagons in all. And 3, 5. Triangles, 5 at every corner. The icosahedron, 20 triangles. That is the entire family, and there's nowhere to add to it. So here is the thing to hold on to. It is not that nobody has managed to find a 6th. It is that a 6th cannot exist. And the reason is not clever geometry. It is that 1 over p plus 1 over q has to beat 1/2, and only 5 pairs of whole numbers do. You did not just see the 5. You saw why there can never be a 6th.